flow, because even if you calculate the, in an ordinary computer, it guides you, the compiler guides you not to overcome, not to overshot the array bounds. So you have to switch this off because this takes as much time as the useful calculation. But you have to be quite sure that you then do not write somewhere else into the memory. And if you do this, you can get a code which is, in a 2D case, an order of magnitude faster than a code that would run without this pointer tricks. And in 3D case, it is even faster because you have even more complex mapping function. So this is something which is much faster, but the problem is that the code is difficult to debug. You can make a number of mistakes over there, and the code is not fast unless you switch off any checks, overflow, array bounds check, and others. So if you switch all that off and you elaborate the code using individual pointers to rows or columns, whether you write that in different manner, you can get a much faster code. I'm quite curious about the time needed for your codes, which some of them are quite advanced. And I will run this and on the same computer and tell you next week what the result was. Possibly you beat it, my code, and then I would offer 2 bottles instead of 1. Now, I have not the results. I will wait for next week for your best code, and we shall see what happens. Gentlemen, questions to my dirty hand implementation into a computer? So when there are no questions at the moment, I would go on with another topic. We have already dealt this equation, Laplace equation, and we have dealt it with finite difference method. What if we have another type of equation which is quite similar to a Laplace equation, but is not exactly the same one? It is also an equation from electromagnetics. And what if this equation is a wave equation? So let's see. We have an equation of the kind Laplace on, I don't know, A plus k squared A is equivalent to 0. This is a kind of wave equation where this is the wave number k. It depends on the material used. Just k squared is equivalent to minus j omega mu times j omega epsilon plus sigma, where j is the complex unit, omega is the angular frequency, 2 pi f, mu is the permeability, epsilon is the permittivity, and sigma the specific conductivity of the material. So we have a complex equation, and this is something we also need to solve. A might be electric strength, flux density, magnetic field, or whatsoever. Now we have this equation, and this is again something which we can solve by finite difference method. So we again cut the area using a rectangular grid. And for any of those points we can again develop a solution which now would again be ready for iterative elaboration. Now, again, if we write down this equation, you'll remember we had a solution to the Laplace equation, which was quite simple, and in fact we got, if we number those points, 1, 0, 2, 3, 4, our solution for a Laplace equation in DC, so in the case we had not this term, was quite simple and was to distinguish between DC and this, I will use the old one with phi, with the potential phi. So we had phi 1 plus phi 2 plus phi 3 plus phi 4 is, and we had there the term which was the second derivative of phi against x plus the second derivative of phi against y, and it was times h square, and we had some reminder there which I would skip now. And this was not complete. There was also 4 phi 0 plus. This is the equation. So having this to be equivalent to 0, because for a scalar potential and static field we have the equation Laplace on phi is equivalent to 0. So this is a sum of second derivatives, which is Laplace in 2 dimensions in Cartesian coordinates. We could say this is 0, okay, and we have an easy equation which says that the potential in the point 0 should be an average of its neighbors. That is quite simple, but when we solve a wave equation, this is no more the truth, because Laplace on the variable a is not 0, but is minus k square alpha. So in fact, we should then get it there. This term would now become this is not 0 now. This is at the moment minus k square, and this is an important point. So if we now would like to get a solution, now I will rewrite this. Instead of potentials, I would put big A to distinguish those two cases. So I will write it into one equation. We have A1 plus A2 plus A3 plus A4, the sum of the values over here, and that is equivalent to 4A0 plus Laplace on A. So that would be 4A0 minus k squared A0, which we can elaborate as A0 times 4 minus k squared. And now to get an equation for a0, we could just divide the whole equation by 4 minus k squared. So we have an equation for updating a0. We should put there not an average, but something that is corrected by the wave number, and that would be a1 plus a2 plus a3 plus a4 divided by 4 minus k squared. So we can use this method not only for static fields, but also fields which are harmonic based on the fact that the frequency is known, can be solved by finite difference method. And the rest of the story is quite similar to what we have already done, so let's leave it as it is. Just a small reminder, a would be mostly a complex number. So this is a short remark on solving harmonic fields using finite difference method. After all, while for static field it's more or less effective, I have not heard for a long time about any paper that used this method for time harmonic fields. So this is added just not to skip it, but anyway, it's something which is old-fashioned and out of date. Well, now we have more or less arrived to a big change, to a new step in finite difference methods, which is very important. We will now come to the method which is now mostly used for solving fields as to solvers that you can buy. I mean general fields in 3 dimensions with general or arbitrary placed dielectrics, boundaries, and let's on. And this is the finite difference time domain method. Now, I think that this is a good time to make a short break, 5 minutes for one coffee, and after that break you will have the possibility to ask questions. Then I switch my papers and start with some story resulting in finite difference time domain. The first thing we should think about is a solution of differential equation. But that's only after the break. So see you in 5 minutes.